Okay, in the previous lecture we have discussed about one relation. Where can I find it? So actually, yes, it's lost, but previously we have talked about the semiconductor charge and function of surface potential. So it has many terms, 6 different terms, and it has different dependencies on the surface potential. So something has some dependencies like this, another one has the other one, and another one has linear dependence and constant dependencies. So also maybe you remember that overall there are different leading coefficient. So for example, 1 or sometimes having ni squared divided by na squared, which can be regarded as an extremely small number. So that's the reason why when we draw our our here density, this is related with our qs term, not exactly equal, so because we have to multiply minus q to this density. But anyway, when we draw it, then it shows quite a dynamic behavior. So of course at flat band the charge itself becomes 0, so that's the reason why we have a very deep decrease here. And another one is if we go to positive gate bias or negative gate bias, we will have negative charge collected in the substrate and positive charge in our silicon substrate. So that is normal. But overall behavior of our density or charge density, collected charge density as a function of gate voltage is not that much linear. So please note that this is just a semi-logarithmic scale. So it means that when up to this point, it is very difficult to see meaningful number of electrons. So let me just go to the more detailed graph written in linear scale. So now this is linear in density, and here x-axis is also gate voltage. When you have a look at this curve, then you can find 2 different curves. One is blue one is green one, and they have different origins. This one is corresponding to the difference between our hole density and Na. So this is related with deflection, and this is solely originated from the electrons. So what we want to have or what we can expect for conventional capacitor, say here we have 2 terminals and we apply certain voltage difference. In this case, for example, in our case, substrate is grounded and we apply gate voltage, so voltage difference across this system is just Vg. Then if this is positive, then we expect positive charge collected in its upper plate, and negative charge collected in our lower plate. This is the conventional case of our MIM capacitor when you have metal, insulator metal. In this case, we expect such kind of thing. So, for example, if we can draw the charge collected in the lower plate here, then maybe what you can expect is, if I apply positive bias, then I will have negatively charged lower plate. So since we are now looking at this lower part, but gate voltage is applied to this upper part, that's the reason why we have inverted sign here. So maybe we will have this kind of behavior. And here we have a slope, and this slope is corresponding to what? It's corresponding to the oxide, our insulator capacitance. If we have a high insulator capacitance, then instead of this original lead one, we will have much steeper behavior here when we have much higher capacitance. And if we have a low capacitance, then we will have a very flattened behavior for our Q versus gate voltage behavior. This is, anyway, you can see that this is just crossing our zero voltage or our origin point, and this is conventional behavior of our IM capacitor, metal insulator metal. However, main difference of our system is now MOS. Yes, oxide is regarded as insulator, so it's okay. But point is, in a lower part, in a lower plate, instead of metal, we introduce a semiconductor. And in the case of a semiconductor, we have two different mechanisms to collect negative charges. Everybody should understand these two different mechanisms. How can you collect negative charges in our semiconductor substrate? One was depletion. So if our p-type substrate is depleted, then it can provide us a negatively charged layer. And another one is inversion. In this case, if we have directly have a sheet of electrons, then of course it can contribute negative charge. So it has two computing mechanisms inside the semiconductor part. That's the reason why now we have a completely different behavior between MIM capacitor and MOS capacitor. In the case of a metal, there is one mechanism, just movement of electrons. This is the only one, so that's the reason why we have a straight line. However, if we consider MOS capacitor, then there are two different mechanisms, and these mechanisms are competing to each other. So that's the reason why when you have a look at this lead curve, please have a look at this overall charge lead curve. This is corresponding to this one. If there is only one mechanism, of course that will show just a straight line like behavior. However, you can see that here we have this kind of quite a strange shape. This one just suggests that there is two different mechanisms. One mechanism showing this kind of behavior, and another one corresponding to just a straight line like behavior. And what is more related with just a conventional MIM capacitor like behavior? Everybody should understand this is more like a MIM capacitor, because this is just a straight line and this is a straight line. So simply speaking, in this case, what we can just roughly say is there is a certain boundary between two different behavior. And for example, around here or beyond this gate voltage, this system just working as usual MIM capacitor, because when we apply further gate voltage, then it increases charge. However, its behavior is shifted from certain gate voltage equal to 0. Even when we go to gate voltage equal to 0, then it does not show exactly 0 charge. So, in order to have really 0 charge in our MOS capacitor, what is the gate bias you have to apply? That was defined as flat band voltage. When you apply flat band voltage, then now you have really vanishing charge here. So this is nothing related with VG equal to 0 volt case, because we have different materials on the top and bottom, and they have different work functions. This work function difference defines this different behavior. So then, since we have two different mechanisms, so when we have a look at Qs as a function of a surface potential, we have to have also terms related with the two different parts. Maybe you can remember two different terms. One related with this depletion was the linear term, and its leading coefficient was just 1. Maybe you remember that one. And another one related with this inversion was exponential, dependent on surface potential, and unfortunately it has quite small leading coefficient. Maybe you remember that. This number is happen to be, for example, 10 to the minus 14, 16, something like that. So extremely small number. However, when we have high surface potential, means that large bending of our energy band diagram inside the semiconductor, then this exponential factor can overcome this small leading coefficient, and eventually this term will overcome this slowly varying linear term. So that is the onset of a new era called as strong inversion. So usually threshold voltage is regarded as the boundary or the voltage where strong inversion occurs. So onset of a strong inversion usually treated or regarded as starting at the threshold voltage. Threshold voltage is typically written as in this textbook Vt. However, we can find many different nicknames or nick symbols: Th, T, Th. There can be so many different variants of T or Th. So don't be confused with this important number with summer voltage. So in this book, Professor Tower's book, always he tried to avoid the use of summer voltage. Instead, he explicitly write down in this way. Well, anyway, you can please try to understand their difference in context. Since you are educated, when you have a look at certain symbol, then you can identify this is related with summer voltage, and this is related with threshold voltage. So anyway, so we believe that at least theoretically, threshold voltage is the voltage where strong inversion starts to occur. So that is the theoretical definition of a threshold voltage. Why I'm saying theoretically again and again? It is because actually it is very difficult to measure the threshold voltage corresponding to our theoretical definition, because our way to define threshold voltage is closely related with strong inversion. And here inversion means that now, although we have applied, or now we have a substrate whose density is Na, so we expect many holes whose density is around Na. However, in this strong inversion case, our electron density is around Na or even higher. This at surface. So once again, we believe that well, since this is a p-type substrate, I can see, for example, 10 to the 17 per cubic centimeter hole density, but actually at surface I can see 10 to the 17 per cubic centimeter electron density. Wow, what happens? It just behaves like inverted polarity. Although we had p-type, but it behaves like an n-type material. So that's the reason why we call it as inversion. But problem is, when we have a real device, we cannot measure the density of electrons at a certain point. So can you do that? So how can you make an MOS system? So on top of a silicon substrate, you grow a very thin, extremely thin oxide layer, and on top of it, you also grow your metal. And this theoretical definition just asks us, please detect the density at this interface. If that is corresponding to 10 to the 17, then that gate bias is a threshold voltage. Then how can you measure the number of electrons at a certain position? Without destroying the structure, we cannot measure it. And even when we destroy it, so we cannot measure it. How can you measure the number of electrons directly? Electrons are invisible to us, so it is almost impossible to detect it. So that's the reason why the theoretical one is just a theoretical one, and we have invented many different ways to actually detect threshold voltage. So please don't be confused with this theoretical value and the measurable values. So sometimes people say that, oh, threshold voltage of this device is, for example, 0.2 volt, 0.3 volt. But you have to ask them once again, what is definition of your threshold voltage? Then maybe they will answer like this way. Maybe in this device, a certain drain current level is defined as to detect threshold voltage, because that is easy to measure. So that is the most important reason why we have this simplified definition of a threshold voltage. But this is related with theoretical one. And once again, now since this is related with the inversion, so what we wanted to have at threshold voltage is simply given as this one. Our band bending is now 2 times of substrate potential. So please note that, yes, let's say that this is our deep substrate. Now we have certain amount of Fermi level corresponding to our p-type substrate, and let's say that this is EI. Then here we so now you can see that starting from this one, now we have a certain energy difference. This is corresponding to Q times phi B. Okay, so now we have band bending, and eventually now, sorry, I have to be more careful. So happen to be, let's say now our ER is almost invisible. Can you see clearly? Yes. So let's say this is our EI. Then please estimate the number or density of holes and electrons. In this case, if this energy difference and this energy difference are identical, then what you can expect is, here we have many holes. And in this case, what we can expect is, now here we have many electrons, and amount of electrons and holes at these 2 points are the same, because electron density and hole density is solely determined by the energy difference between our Fermi level and intrinsic Fermi level. So if we set the same difference, only different polarity, then what we can say is, okay, electron density at 0 point is equal to hole density at infinity point. This is the relation for our inversion, onset of strong inversion. Now electron density is equal to the substrate hole density, and beyond, this is the case where gate voltage equal to threshold voltage, and if we apply gate voltage even higher than threshold voltage, then we will have a higher band bending and electron density will increase further. So further increase means that now we have full electron densities nearby this oxide silicon interface. So this is the case. So please remember that we have to have 2 times band bending. Why we have 2 times band bending? This number 2 is used in this way. Number 1 is just bending, so this EI into Fermi level once, and another one is used to further bend it to the downward to the same amount. So in order to invert it, we need it twice. Let's simply think about this one. You have number 3, but in order to make its inverted value or negative value -3, what you have to do is first reduce it by reduce to 0 and reduce it to -3. So this is corresponding to 2 times band. 2 times phi b is required for your overall band bending. Okay, so now we can divide this QS over phi s into 2 meaningful representative operation regions. One is depletion region, and another one is a strong inversion region. Please note that we have so many terms. However, some of them have exponential dependence, and some of them is linear dependence, and some of them are just constant. So their relative magnitude can vary quite a lot. So by applying certain range of our surface potential phi s, some of them becomes really insignificant. We can neglect them. So among 6 of them, some are deleted. So then we can find very good approximation about simplified approximation for QS over phi s. This is practically very important. So maybe at first glance, now you have exact expression, 6 terms. Wow, with this exact equation, you can solve that system exactly. Perfect. However, in order to solve that system, always you have to consider non-linear behavior of your equation, because your equation just follows square root of something. And something contains exponential function, another exponential function, linear function, and also constant numbers. So it is very difficult to get this number efficiently. So that's the reason why we wanted to make approximation. So please do not hate these approximations. Approximations are at the heart of our engineering life. So this is really important to introduce valid approximation and good approximation to our exact solution. Okay, so first one I will talk about is depletion approximation. So in the next slide, I will just show the more general way. But for a while in this slide just to do it as we did in our PN junction. I will assume that there exists certain how can I say depletion width, and in this depletion layer we have completely depleted interface region. So since we have Na and it is negatively charged, so now we have minus Q times Na as a space charge density. So in other words, in our law is given as minus Q times this number. So then what will happen? So if we have this kind of behavior, then simply speaking, our divergence of electric field is given as low. That was our Poisson equation. Maybe you remember it. So by integrating this number, integration of our electric field, now we can find, so simply speaking, if we just write down 1D expression, then it means that the first order derivative of our electric field is simply given as minus Q times Na divided by silicon permittivity. That's it. So starting from certain surface potential Es, there will be negative slope, and this slope is corresponding to minus Q and A times epsilon silicon. This is nothing but I'm just to write down our Poisson equation, and eventually it will vanish, and according to our depletion approximation, that position will be a depletion width. So let's just say we have a little idea about what is ES value. Actually, ES value will be determined by our gate voltage. If we change gate voltage, then that can increase or decrease this surface electric field. But anyway, once this number is given, then this decreasing slope is just defined as our doping density. When you have high doping density, then please try to estimate its shape. If you have a high doping density, then it will behave this way. If you have low doping density, then what you can expect is, okay, this would be the behavior of your electric field. Okay. So anyway, now we have a given decreasing slope, and let's say this is a WD, then product between this length scale and that length scale will is potential difference between this point and that point. I'm just showing you this equation following that one. So potential difference is given as product between this WD and ES. And what is ES? This is the expression for ES using this linear given constant slope. So are you with me? So now you can see that WD can be depletion layer thickness can be simply written as a square root function of a surface potential. It means that if we have high bending corresponding to high surface potential, then depletion width will increase. In order to increase twice wider depletion width, what we have to do is 4 times higher bending. If we have 4 times higher bandbanding, then since we have a square root here, then we will have 2 times wider depletion width. So it is, maybe you can expect that maybe it is very difficult to have extremely wide depletion layer, because if we already have a certain depletion layer, after that, in order to increase it by amount of 2, yes, say that this is your given WD and given phi s. In order to make it double, 2 times WD, actually your bandbanding should be 4 times phi s. So it is really difficult to introduce such kind of high bandbanding, severe bandbanding. So it is easy to guess that increase of our depletion layer is much limited. We will see it quite soon. So anyway, since we have approximated form of depletion width by applying this minus q times Na, this is the space charge density, so we can easily collect the depletion charge we have. So simply speaking, this is nothing but square root function of surface potential. If we have surface potential higher and higher, then we will have more and more depletion charge, but it's not that exponentially increasing. So this is a slow function. Up to now, in this case, I just show you the discussion starting from this simple approximated electric field form, but instead of that, let's start a more rigorous way. Here, you have one expression. What is it? This is nothing but the slightly changed form of our QS versus potential, surface potential. So instead of this surface potential, now we have electric field or d phi over dx, but it is completely okay because we can just convert it by multiplying our permittivity value. So when we have gate voltage higher than flat band voltage, yes, this is the condition we conventionally consider. So please note that flat band voltage is about minus 1 volt, and our gate voltage is almost always higher than minus 1 volt. So we can fix this sign. When we have gate voltage lower than flat band voltage, then actually we have a sign difference. So we must have positive sign here. However, practically, we always apply gate voltage higher than flat band voltage. So it is completely okay to keep this negative sign. Then now you have 6 different terms. And what I wanted to ask you is, please try to keep only important terms when we have this kind of typical condition for our depletion approximation. Surface field is at least higher than summer voltage. So maybe it is not that difficult to get this condition. If we apply, for example, flat band voltage plus 2 over 3 times of kBT over Q, then we can easily achieve this condition. I mean that since flat band voltage is around minus 1 volt, so if we are talking about 0 volt or minus 0.1 volt, all kinds of our interested gate bias is corresponding to this condition. We can say that our surface potential is always higher than summer voltage. It's okay. However, there is more significant condition. Now we say that this phi s is lower than sufficiently lower than 2 times phi b. Why do we have this condition? If we have band bending equal to 2 times phi b, then it means that this exponential term combined with this extremely small leading coefficient now becomes comparable to the other terms appearing in the first part. So that's the reason why we introduce this condition for depletion approximation. So by applying this condition, so surface potential is way behind this 2 times phi b, so we can eliminate this entire term without any difficulty, because this leading coefficient is so small and this exponential function cannot overcome that small leading coefficient. So of course these guys are not grow quite rapidly, so we can safely neglect it, and this one is the best one. However, even this guy cannot overcome this small coefficient. So this is second parenthesis, entire parenthesis can be neglected. That is one thing. And how about this first term? Yes, in among first term, here we have exponential minus exponential function of surface potential, but you know, in our case, beyond the flat band voltage, always surface potential is positive. So minus exponential function rapidly approaches to 0, so we can neglect it. So why it is neglected? Because we have assumed that gate voltage is more higher than flat band. In other words, our surface potential is positive number, so we can neglect it. And another one is here we have a minus 1. There is not that much reason we must neglect this minus 1 term. For example, if we say just 0, then we have to keep it. But you know, since we have assumed that, so surface potential is way higher than summer voltage. So when we make a comparison between this one and that one, of course it is higher than number 1, so we can neglect it. Well, let's say phi s equal to just 2 times kBT over Q. Then can we neglect minus 1? Actually not. So if we neglect this minus 1, then this overall number will become just number 1. However, if we neglect this minus 1, we will not have a number 2. This is a huge difference. However, actually what we expect is surface potential is much higher than summer voltage. So band bending is much higher than summer voltage, so we can safely neglect this minus 1 term. For example, 40. 40 is too high. 20 and 20 and 20 minus 1, 19. So they are just treated as comparable numbers. So maybe if you don't like it, then please keep it. But then maybe your equation become more complicated. So this is the approximation. So now, since we have only one term remaining, so now we can say that deleting all negligible terms, then now we can have quite a simple form. d phi over dx is just given as square root of surface potential. So now we can solve it. Then by solving this one, we can have exactly the same expression for our depletion width. So either way, it is completely okay. So up to now, we have just introduced the depletion approximation, and it's electric field versus position is given as just a straight line. So potential is obtained as integrating this electric field once again. Since this is a straight line, we expect that when we draw potential versus position, then this is linear, and we will have parabolic function of x that is shown here. Now you can see that if we just consider potential profile, then we will have a parabolic behavior here. Well, if this electrostatic potential is the one defined by Professor Tauer's notation, then we cannot have this non-zero value. When we talk about phi in short courses, lectures in our last lecture and second last lecture, we say that here we have 0, phi equal to 0, and we had such kind of behavior. So that was regarded as, this difference was regarded as surface potential. When I draw here in this slide, I'm just to write down non-zero value, and it is regarded as a phi b. Actually, this exact value is given as minus phi b. It means that this electrostatic potential is not the one for Professor Tauer's book, but this is the normal one, usual one, which is satisfy n equal to ni exponential phi and summer voltage. Please note this one. Okay, so are you with me? If we follow Professor Tauer's one, then we will have this exponential function. However, now we have this quite a small exponential function. Okay, quite a small leading coefficient. So because these two numbers are having the offset between them. Okay, so anyway, we can have a parabolic potential profile. That's the reason why in many cases, when you have to draw your energy band diagram, what you have to draw for your MOS capacitor, your energy band should be drawn in this way. So at deep substrate, of course, you have to draw a straight line. So because this is neutral. However, beyond this point where you have a depletion, then what you have to do is just to draw parabolic line. So if somebody just to write down in a straight line, then well, it's not that much correct one. You have to draw this parabolic one, and this parabolic one, this end of this parabolic behavior occurs at depletion width. So are you with me? So please. But sometimes it is difficult to model this kind of parabolic behavior. Sometimes people say that actually, even though it is parabolic, but electrons are almost always found only at this point. Can you find a sufficient number of electrons at this point? No, because why? Because here, let's say that this is, for example, conduction band level, then our Fermi level is more or less attached to here. So even though here we have a parabolic variation in our conduction band level, but energetic difference between Fermi level and conduction band level is already too high, so we can neglect electrons. So in terms of the experience by electrons, this part is almost nothing. So what sometimes people just approximate it as this straight line. Then what is the slope for this straight line approximation? That approximation should be done for this surface part, because this surface is where electrons are actually found, and the linear slope felt by electrons are the one by this surface region. So you must understand this kind of behavior. Sometimes we apply this kind of approximation, but only we must use it wisely, not blindly. Okay, so now in this case, so since we have parabolic behavior, if we go to even higher surface band bending, then we will have wider depletion region, and if we go to even higher band bending, also we will have a wider depletion region. However, we have a maximum depletion width. It is because depletion width and surface potential, of course here we have two, but surface potential 2 times phi s is required, and phi s cannot increase indefinitely. For example, what is the maximum value of our phi s in our usual operation? Can you expect 10 volt in your surface potential? So you never expect such kind of a high value. For example, can you expect 2 volt? Never. You never have it. The maximum value of phi s you can expect in reality is at most around 1 volt, slightly higher. It is because this is related with entire band gap. So band gap divided by Q will give you just 1.12 volt, and your surface band bending cannot exceed this value, because it is to understand. So since this surface potential is more or less bounded up to just 1.1 volt, so since this is bounded, also your depletion width is bounded. So you cannot increase your depletion width any further, and more or less this value is given as just to insert the condition for onset of strong inversion. So then this will be the approximate value for your maximum depletion width. It is supported by numerical simulation here. This blue line is corresponding to the depletion charge, and depletion charge can be converted into thickness of our depletion layer, and you can see that beyond some point it does not grow any further rapidly, almost fixed to a constant value. Of course, we should be a little bit careful. If we magnify it, then you can see slight increase in this case. For example, let's come back to our linear scale. When you come back to the linear scale, I think that here, where can you find this depletion charge? Yes, this blue line is corresponding to our depletion charge. And can you see almost constant behavior? yes, we can see it looks like just a constant. Yes, so we can see almost constant, but if we can magnify it, then you will see really really almost flat, but slightly increase as a function of a gate voltage. But you know, here we have a really drastic increase of our inversion charge density. So compared with this meaningful variation of electron density, this can be regarded as almost constant. So that's the reason why, without much degradation of accuracy, we can say that depletion charge or depletion width has its maximum value and it is just saturated, no longer increased. And if we go to beyond the threshold voltage, so beyond the threshold voltage means that now if we have even higher band bending than 2 pi kb, then what will happen? Let's just consider. If we have phi s equal to 2 times phi b, then what we can expect is electron density at interface becomes just the whole density at deep substrate, and it is corresponding to Na. This is typically quite high number, 10 to the 17 per cubic centimeter, 18, not 19, but 18 or 17. So this is a quite high number. Now, let's say that we have introduced even higher band bending. I mean that here I just introduce delta phi. This delta phi can be 1 millivolt, 2 millivolt, or 0.01 millivolt, not like 0.1 volt, 0.2 volt, relatively small value. Then what will happen? If we introduce this additional band bending to our energy band diagram, then what we can expect is now our electron density will be just given by Na times exponential delta phi divided by summer voltage. Are you with me? So simply speaking, if we just increase this delta phi by amount of 1 summer voltage, then we will have, instead of just 10 to the 17, we will have 2.3 times 10 to the 17. This is a huge increasement. So once we have the inversion, strong inversion case, then small amount of additional band bending introduce quite large increase of our electron density. So now we go to the eventual answer of our question. Our eventual question was, what is the division rule between oxide and semiconductor? When we apply certain voltage beyond flat band voltage, when we apply certain voltage deviated from flat band voltage, then we will have division, additional voltage, and they should be divided into two parts. One part was oxide potential, and one part was surface band bending, surface potential. And now, when we go to this strong inversion condition, then now this guy at strong inversion case, at least to have a strong inversion, it must have 2 times phi b. Yes, this is the requirement to enter into the strong inversion regime. After that, if we introduce extremely small difference in this surface bending, surface potential, then we can supply much high additional negative charges. Now our substrate becomes a superpower. So by changing surface potential only a little bit, it can provide a lot of electrons or negative charges in this point. However, please note that we have another guy called as oxide. Oxide is just linear. In order to collect more negative charge, it should have additional linear dependent potential difference. So it is always just steady. So if we have linear potential difference, then that is just collecting that amount of additional charges. So simply speaking, now when we consider this one, now we have certain delta V ox, then we can have this amount of charge collected by our oxide layer. And now in the case of our silicon substrate, then with quite small delta surface potential, we can collect many electrons. So that's the reason why when we additionally introduce delta Vg into our gate voltage, almost all delta Vg is assigned to our delta V ox, because in order to match these two different mechanisms, one is oxide charge and one is silicon charge, but anyhow they should have same behavior, they should describe same behavior, the charge collected underneath the oxide layer. So if we assign too high delta phi, then substrate says that, oh, I can collect so many electrons additionally, it's not that difficult to me. But oxide says that no, if you take too much voltage, then there is nothing left for me, so I cannot match your sharp increase in electron density, so we cannot have a balance. Balance is important. So in order to have the balance, actually in this strong inversion regime, almost all applied gate voltage should be assigned this oxide feed. That's the reason why people say that, okay, beyond the strong inversion, actually surface potential cannot grow any further. Don't be confused with this statement. Not exactly fixed to this 2 times phi dB, but it does not grow significantly. I mean that it does not add it to 0.5 volt. No, it is just increasing 1 times the summer voltage, 2 times the summer voltage, 3 times summer voltage. Of course, it can increase even 0.1 volt. Yes, this is a somewhat large variation, but please think about the journey of our surface potential. When it was biased at gate equal to 0 or even lower gate bias, surface bending was so marginal. However, when you apply gate voltage, so in before strong inversion occur, actually this band becomes quite much more banded by increase of our gate voltage. But after that, after strong inversion occurred, its behavior further increase is much limited, and it is, although it is increasing, but it's its amount of increase is really limited. So let me just explain a little bit further with equation. So now think about strong inversion case. Strong inversion case means that phi s is now higher than 2 times phi b. In this case, what are important? So let me just come back to our equation here used for, yes, so let's have a look at this one once again. Now think about the strong inversion case. Which guy is important guy? You know, this one exponential function always doesn't play any role. And also we can neglect this minus 1. And now this number is quite important. However, compared with this exponential term, still this one, they are not important at all. So what we can expect is in this strong inversion case, this guy is still important, and this guy, oh, so I didn't mean it. Well, okay. So now this guy are important. So now let's come back to this one, strong inversion. So now we must keep these two numbers. One is this one and another one. This one is related with what? Related with still related with the depletion one, and this one is related with our inversion related quantity. So maybe you can ask me, oh, if that is so important, why don't you just kick it out? So it is not possible, because we must keep this still this depletion charge. And now, then why we must keep this charge, depletion charge? Exponential becomes too high. Now it is rapidly growing, and this one is just slowly increasing. And now we are at the strong inversion case. But why we have to keep this guy exponential? The reason is, of course, when we have phi s equal to 2 times phi b, these two terms becomes comparable. However, when we additionally add phi delta phi, if we can increase this delta phi indefinitely, then of course this guy doesn't play any role. But point is, you know, further increase of surface potential is quite much limited, because surface potential is almost pinned to 2 times phi b. Only small difference like 0.1 volt or around this number is allowed it. So compared with this term, this one does not grow dominantly. So although this guy becomes much higher than this one, still we have to keep this depletion related term. Okay, so are you with me? So that's the reason why we must keep these two numbers. Of course, once again, if we can send phi equal to infinity, then of course we can eliminate it. But that condition cannot happen in our MOS case, because phi s is pinned to 2 times phi b. Once again, don't be fooled by this term called as a potential pinning. Pinning means that it doesn't change at all, but it can, although it can increase, but its increase is quite slow. So please. So here I have prepared one simple example. Now surface potential is corresponding to 0.85 volt. let's say that this is a strong inversion. So here you can see that the surface electron density is corresponding to 2 times 10 to the 18 per cubic centimeter. Yes, now we have a strong inversion, and we just increase surface potential by amount of 30 millivolt. Yes, 30 millivolt is roughly 1.2 times thermal voltage. So because thermal voltage is 25 millivolt, 30 millivolt is just 1.2 times of thermal voltage. And what you can get is here, roughly, this is corresponding to 7 times 10 to the 18 per cubic centimeter. So just to introduce 0.03 volt additional surface bending, now you have much higher electron density. So now your substrate becomes quite sensitive to the additional surface potential or band bending. So all applied additional gate voltage is applied to your oxide layer, because now please allow me to make a certain. There are two guys, and they are banded, and they have to move together. And this guy doesn't work quite well, and this guy, the world fastest guy, then what will happen? If this guy is so fast and this guy is so slow, then overall behavior is limited by this slow one. It's like this. Here we have oxide and silicon substrate. Now beyond strong inversion or threshold voltage, now this substrate becomes really sensitive to the potential difference, so it can provide a lot of electrons quite easily. However, this oxide guy is always just steady, and same amount of potential difference can be converted into also same amount of charge difference. So all kinds of their overall behavior is now limited by this slow guy, yes, like oxide. So eventually, simply speaking, beyond threshold voltage, the behavior of this system, MOS system, is determined by just oxide. So oxide capacitance becomes the dominant capacitance we will see from our MOS system. But if we go to the gate voltage lower than threshold voltage, then what happens? Now the guy shown here, called as a silicon substrate, becomes a dull one. So I become quite slow, so please, now the overall procedure is limited by this silicon substrate. So that's the reason why we have two phases of our MOS system. So we are actually using these two behaviors. It is really important to have these two different behaviors. Why? In a device application, actually having current conduction is not that difficult. If you want to have a real current conduction, just build a structure with only metals. Once you have a system only made of metals, then you can conduct quite a lot. Great. But point is, the system, our electronic system, should be controlled by our voltage signal, sometimes we should be able to turn them off. That is the real capability. Sometimes when you want to turn them off, they should not conduct. How can we get such kind of a shutting down our devices? That is important. So only this kind of a behavior can be achieved by our I'm exaggerating, but anyway, this kind of a two-phase can be provided by our MOS, because MOS, first, at its low gate bias, it provides certain negative charges, but these negative charges are immobile one. So please, what was the physical origin of negative charge collected under the oxide field, oxide layer before threshold voltage? When we have gate voltage lower than threshold voltage, although we can collect negative charge, but this negative charge is just obtained by holes. Actually, depletion of holes. So at the surface of our MOS system, oxide and semiconductor, now when you have such kind of thing, now we have no mobile carriers at all. Although we have negative charges, but it is not corresponding to the negatively charged mobile carriers. There is no carrier at all. So we are using this condition to shut down our devices. But if we go to gate bias higher than threshold voltage, then now we have very high density of electrons and they can move. So they can be used to conduct current. So by using these electrons, we introduce current conduction. So once again, since we have two different mechanisms, we can separate them, and fortunately one of them is not very good for current conduction and we love it. Sometimes turning the device off is more important than turning the device on. So that's the reason why we can have a quite good off current condition. We can reduce the amount of current when we do not want to turn this transistor on. Okay, so I'm sufficiently repeated so many examples to emphasize the beauty of MOS system. Okay, so two mechanisms, and only second mechanism called as inversion can provide us mobile carriers. That is quite important. So let me just wrap up explaining this session with explaining this graph. Up to now, I have told you that the theoretical condition to have strong inversion, onset of strong inversion is electron density at interface becomes Na, or the hole density at deep substrate. This is a theoretical one. However, even theoretical sense, this condition cannot be actually satisfied, because if we go to a little bit further in device physics, actually oxide and semiconductor interface can be regarded as potential barrier. So from the viewpoint of our electrons, actually what they can feel is like this. There is almost infinite potential wall, potential barrier. Its value is about 3.1 eV. So please think about gas 3.1 eV, because it's the electrons, from the viewpoint of its electrons, its energy scale is more or less given as kBT. Thermal energy is the energy scale we can have. Like I'll give you one summer energy. Oh, thank you. And these are just living over these normal electrons. But you know, 3.1 eV is roughly corresponding to 120 kVt. 3 electron volt is corresponding to 120 eV. So from the viewpoint of them, their viewpoint, it's like a so it cannot overcome this barrier. So this exact interface between oxide and silicon, this point should be regarded as a clip for our electrons. So it's like this hard wall. So if I just hanging around this entire room, then maybe you may have quite a small probability to find me in this position, because you know I cannot penetrate into this wall, so I don't want to stay here and slightly away from this wall. So that's the reason why actually electrons density at this point n equal to 0 cannot exactly the whole density at deep substrate, actually equal to quite close to 0. And peak point is not exactly found at x equal to 0, but its peak point is slightly found at slightly deeper side. So that's the reason why, please have a look at this one. Here you have a lead color. This is a lead one, but this is empty. And this one is a lead one, but that is filled. And what are the difference? When we consider this effect, electrons cannot exactly attach to the potential wall, potential barrier, then you can have this difference. So, but the theory we have studied up to now cannot consider this effect, and this is beyond our study up to now. So if you are interested, then please do your study. But we have to understand our consideration is related with these empty ones. Then long estimation, yes, this is long, but how can we use it? Of course, we can just slightly calibrating our parameters to fit the actual property. So maybe you feel that, then it's very bad habit to fit everything to match experiments, but this is the real life and engineering. So okay, so I would like to wrap up today's lecture, and if you are interested, please come to me. I can give you more answers, examples. Thank you.